Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking a little bit about potential energy. So at this point, if you've been watching these in order, you have already seen my videos on both work and kinetic energy. So you might recall that we've defined work as work is force dotted with displacement. So that would be like force along x, delta x, and force along y, delta y, and force along z, delta z. You'll also recall that we said that the net amount of work was equal to the change in an object's kinetic energy, where the kinetic energy is defined as 1/2 the mass times the speed squared. At least the translational kinetic energy is. So in this video we want to add one more piece to the description for energy. The idea being that this is a net amount of work, but you can have certain forces that you work against that are just kind of like always present. And in some cases, you do work against the force and you get nothing for the work. You just kind of are able to maintain an object's motion. But in other cases, you sort of store up energy when you do work against the force. So an example of the former would be friction. If I have friction present and I push a block and I walk along and I keep it going at a constant speed, but I'm having to push to keep it going, I'm doing work on the block, friction is doing work on the block, and the two of us are kind of working against each other. In other words, our forces are opposed, and the end result is that you don't have any increase or decrease in the kinetic energy, assuming that the two forces are balanced. And if I stop pushing on the block, it stops moving. In the end, you kind of maybe heat the bottom of the block and heat the ground and get some sound waves and so on, but you've lost mechanical energy from your system. On the other hand, if I have an object and I lift it up off the ground, so maybe this is some mass, here's the ground, and I lift the object up into the air so that the object ends up some height above where it started from. In this case, if I draw a free body diagram for the object, I would have gravity acting downward. So this would be the mass of the object times g. And I would have whatever force I'm using to lift it with, we could call this F lift, acting upwards. Now in this case, if I'm doing this at a constant speed, F lift is equal to the opposite direction and equal magnitude of gravity. So the net amount of work in this system would equal 0. However, in this case, if I were to then have the object up here at the top and suddenly release it so that it could travel back down to the ground through that same height h, then in this case the work being done would be entirely due to gravity. The only force present is gravity acting downward on the object mg. And so upon release, I could get, or can get, a total work W is equal to mg times h when it hits the ground. In other words, despite the fact that the net work on this object is apparently 0, by the work and kinetic energy theory, there's no change in the kinetic energy, there is a sense in which work was done on the object, and we can get that work back. So the object falls back to the ground, we get mg times h. And notice that if I came over here and looked at how much force, how much work is done in lifting it, W lift, so taking this force in isolation, I'd have F lift times h, but that would just be mg times h because the lifting force and gravity are equal. So this means I've basically stored energy in this object by lifting it to a higher position, and I can get that energy back. So this stored energy, we could say stored energy that is generated by working against a force within a system. The stored energy that we generate by working against gravity or some other force like gravity can be recovered by essentially releasing the object. So this is potential energy. Okay, so potential energy, we typically use either a capital P for potential, or a lot of physicists like to use, for classical physics, a U. And the way that potential energy works is you have to have a force like gravity, not like friction, but like gravity, that you can do work against. And so there's kind of two kinds of forces. There's forces like gravity, which are what are called conservative forces. And so gravity is one example. The Coulombic force, which we encounter in Physics 2, is another example. Hooke's law force from a spring is another force that's conservative. These allow potential energy. So these allow energy to be stored as potential energy. And other forces like friction, so non-conservative forces are what they're called, non-conservative. And these would be like friction, drag, stuff like that. Force that you yourself apply. So sort of like, we could call that artificial if you'd like, because it's being created by you putting a force. These do not allow energy to be stored. So these don't store potential energy. So that's an important distinction to make. So now, potential energy, how might we define it? So one simple definition, a practical definition that I like to use, this is not the formal definition, but it's a good practical definition, is that potential energy is the potential for a conservative force within a system to do work on some object in the system. I will say that again. Potential energy is the potential for some conservative force in a system to do work on an object in the system. So if you want to figure out how much potential energy is being stored by an object, then kind of imagine like you're trying to figure out how much work would be done on that object by some conservative force, say gravity, if the object were allowed to move freely along the direction of that force. In other words, if I drop the object and it falls straight down, how much work would be done by gravity? Before we move on to clarify this point, what are the units of potential energy? Well, it's another type of energy, so like kinetic energy and like work, it has units of joules. Okay, so coming back to this idea of how much potential is there to do work in a system, the answer is it kind of depends. And the reason why I say it kind of depends is because when you are setting up potential energy within a system, you defined where your sort of ground is for the system. So when doing work with gravity, in some sense, gravity stops doing work when the object stops by hitting the ground. But your definition for where you want to call the ground is kind of up to you. It's a sort of preference choice. For example, if I am going to drop an object that I'm holding in the air, and there is a table somewhere, and I'm going to drop it so it lands on the table, then I might define this right here to be the height, and so this is height equals 0, the ground. But we know from experience that this object could land on the table and then bounce off and hit the floor somewhere. And so the floor ends up having height less than 0, a negative height in this sense. So work is continuing to be done, but we would say that essentially the object has gone from a positive potential energy to a negative potential energy. So we might say U is less than 0 here, and U is greater than 0 here. We could also redefine the floor to be our height equals 0. So I'm going to draw that in blue. Alternatively, H equals 0 here, and so this right here would be like H1, and this right here would be like H2. Notice that this means that U is greater than 0 here, and U is greater than 0 here, and U equals 0 here on the ground. So what is it that matters? Is it the potential energy itself that matters? No. It's actually changes in potential energy that we really care about. So this is another of those very important points that kind of deserves a box about it. We care more about the change in potential energy and moving from point A to point B than we do about the potential energy itself at either of those points. Second item is that you have to define where the ground is, or in other words, where potential energy is 0. Okay, in defining the ground, you've done the equivalent of choosing where you're going to call H equals 0 and therefore U equals 0 when we're dealing with gravitational potential energy. In general, you're defining where is U equal to 0. Is it down here or is it up here? Notice that for either choice, our delta U is the same. So delta U is the same for all ground choices, given the same starting and ending points. So for all ground choices, given, let's say, start and end, remain the same. So that's the other important point about potential energy. Okay, let's go ahead and work one example that's really kind of two examples that ties all this together. All right, so in this example, you've got a 1 kilogram mass, you're holding it 25 centimeters above a tabletop, and the tabletop itself is 85 centimeters above the floor. We want to get the potential energy, the gravitational potential energy of this mass relative to the tabletop, and then also relative to the ground. That means to the floor. So the diagram is basically this diagram I drew on the previous slide. To get the potential energy, we'll say U relative to table. This would be mgh relative to table. So that's 1.0 kilogram times 9.8 newtons per kilogram times 25 centimeters times 1 meter per 100 centimeters. All right, so that is basically 0.25 times 9.8 times 1, which should be 2.45 joules. Now do relative to the floor. So this would be m times g times h relative to floor. And so again, we have 1 kilogram times 9.8 newtons per kilogram times, and if we convert both of these to meters, this is 0.85 meters, this is 0.25 meters. So this is 0.85 meters plus 0.25 meters. All right, and so this is 1.1 meters. And therefore, my potential energy relative to the floor is 9.8 newtons per kilogram times 1 kilogram, so that's 9.8 newtons times 1.1 meter. So that should give me basically 10.78 joules. This would be 11 joules at two significant figures. At two significant figures, we have 2.5 joules up here. For our second example, what we want to do is take the same situation and say, suppose you drop the object so it falls down onto the tabletop. And what we want to get is the change in potential energy considering the ground, considering the floor as the ground, and also considering the table as ground. So table equals ground. In this case, our change in potential energy, so delta U is mg height final minus mg height initial. So in other words, this is going to be mg delta H. Now in this case where the table is the ground, H initial is 25 centimeters or 0.25 meters, and H final is 0. So plugging all those in, you actually will get the same answer as we got here when we found the potential energy relative to the table. So we should get 2.45 joules for the delta U. Now let's take the floor as ground. If the floor is the ground, then the same delta U is mg times height final minus height initial is still valid. That's mg delta H, or mg H final minus mg H initial. That's still a valid equation, but now my initial height is this height above the floor, which again was 1.1 meters. So we have 1.10 meters. Okay, our final height, height final, was 0.85 meters. That's the height of the tabletop above the floor. So my delta U in this case is 1.0 kilograms times 9.8 newtons per kilogram times 1.10 meters minus 0.85 meters. So this again is 0.25 meters, and so I get as a delta U 2.45 joules, the same answer as what I got for this previous case. So delta U is the same in both cases, even though the initial potential energy is different in both cases and the final potential energy is different in both cases. All right, so that's all that I'm going to do in today's short video. Hopefully you've learned a bit from watching it, and thanks for watching.